Hello, welcome to a video on section 3.6 discussing matrix multiplication. So the last video was on matrix addition and subtraction and distribution, and those are pretty easy. The arithmetic for matrices shouldn't be too challenging, pretty straightforward. Multiplication could be a little challenging, so we're going to talk about that right now. So say, for example, we have two matrices, we'll call them A and B, and we have the columns and the rows defined for each of those matrices. So matrix A is an n by n, matrix B is an n by p. Now, in order for the multiplication to happen, here's what you have to do. You have to make sure that the columns of your left matrix, we call that A, and the rows of your right matrix, call that B, are the same. So, for example, matrix A is an n by n, matrix B is an n by p. So when I do A times B, I have an n by n with an n by p. And we need those two numbers, the columns of the left matrix must equal the rows right matrix. If they don't, then we can't do the multiplication. We have something called a dimension mismatch. This will be more clear when I actually show you an example. But before we do that, we'll just state if we can do this. So state where the product AB is defined. So notice how those don't match up. The answer is no. Now notice how those match up. The answer is yes. And the dimensions of your answer will be a 3 by 2. Now, again, you kind of just take my word for this. Let's actually go through an example so you see how this works. So I'm going to skip ahead. I'm going to skip ahead a little bit, and let's take a look at maybe example 2. What if I do A times B and then A times C? So I believe this is page 13 or 14 of the notes. Let's see where we are with these notes here. Yeah, page 13 and 14. But we're looking at page 14 because I'm going to the end here. Okay. So if we do A times B, A is a 3 by 2. There are 3 rows and 2 columns, and I discussed in the last video about how to determine the rows and columns. Really easy, 3 rows, 2 columns. The 1, 2, 3, the 2 columns, and B is a 2 by 2. So the multiplication can happen. And I'll show you how this works. So here's A, here's B. What we're going to do is we're going to multiply the first row with the first column. So I'm going to do 4 times negative 3 plus 3 times 1. Notice I'm doing 4 times that number and then 3 times that number. And then I'm going to add the results. Then I repeat that, but now I'm multiplying the first row with the second column. So 4 times 0 plus 3 times negative 2. Now I'm going to do this again, but with the second row of the left matrix and the first column of the right matrix and the second row of the left matrix to the second column of the right matrix. So I'm going to do negative 1 times negative 3 plus negative 2 times 1. So it's kind of a pattern. Negative 1 times 0 plus negative 2 times negative 2. Then lastly, I'm going to do the third row with each of the columns in the right matrix. So I'm going to do 2 times negative 3 plus 0 times 1, and then 2 times 0 plus 0 times negative 2. Notice how what's going to result when I go through all this multiplication addition and the answer that I'm working out, it's going to be a 3 by 2 matrix. That's because if I look at the outer dimensions of what I'm trying to multiply. So now I look at the rows of the left matrix and the columns of the right matrix. That's going to define the product. So the rows of the left matrix and the columns of the right matrix will define the product. So if I work it all out, I should get, I think, negative 12 plus 3 is negative 9, 0 plus negative 3 is negative 6, 3 times 3 plus negative 2 is 1, 4, negative 6, and 0. And there's a way you can do this in the calculator. We'll talk about that in class. But that's why we care about the dimensions matching up over here. Now, if they didn't match up, say, for example, I try to multiply b times a, like in this case right here, right? Here's what's going to happen. B is negative 3, 0, 1, negative 2. Here's a, 4, 3, negative 1, negative 2, 2, 0. So we're multiplying 2 by 2, 3 by 2. There's a mismatch. This can't be done. It's not possible. Because if I try multiplying the first row here with the first column of the right matrix, well, fine, I got negative 3 times 4 plus 0 times negative 1, and there's no one multiplied to the 2. The 2 is all alone. It's by itself. Nothing you can do about it. So this can't be done. So you have to make sure the dimensions match up. So that's why looking at this example, there's there's a mismatch, right? But here we do have a match. Now, it can be useful in business applications, and we are going to talk about solving system equations in this manner. But here we're going to have two matrices. I guess our inventory matrix, our cost per item matrix, and it's going to be total cost. It kind of makes sense, right? Inventory is how many items you have, and the cost per item multiplied together, you can see the total cost. Like if you got 10 items and each of them costs $2, that's $20, right? Very simple. But what if we have a lot of items, right? And we have all these different costs? Then it's going to be good to actually organize the matrix. Let's look at the example down below. So Coach G submits a request for equipment for our women's hockey team and men's hockey team. And so here are the equipments that both women and men need, and the costs for each item is right here. Here's what I'm going to do. I'm going to make myself a 2 by 3 matrix. Yeah, 2 by 3 matrix. Women and men, sticks, pucks, and uniforms. And I'm going to make a 3 by 1 matrix with the cost, but I want to make sure I go in order. So sticks, pucks, and uniforms. That way things are going to match up very nicely. Notice how we have a dimension match. The columns of the left matrix will equal the rows of the right matrix. So let's write out all of our inventory. 14, 30, 18, 16, 25, and 20. And it's very important that I organize the cost per item matrix, the right matrix here, as a 3 by 1, so I have that dimension match up. So the dimensions match up. Because here's what's going to happen now. When I actually multiply it out, I'm going to do 14 times 60, 30 times 2, 18 times 35, and add it all up. Because 14 should be multiplied by 6. Those are both the sticks, right? 14 sticks, $60 per stick. Plus 30, we're adding because we're, find the total here. 30 times 2 for pucks, 80 times 5 for uniforms. That's for the women. Now we do the men row. 16 times 60, plus 25 times 2, plus 20 times 35. So this could be a great way to really efficiently get the total cost, especially when you start dealing with hundreds of items and all these different costs. In fact, believe it or not, Amazon.com, this is how they actually organize their database. They probably have one of the most elaborate databases in the world. It's the most expensive company in the world, valued very well. The stock is done amazingly well. As I'm typing this, as I'm making this video, I could probably just go on Amazon on my phone and order something. But how do they have all that crazy stuff organized? They have the matrices. And it's so much easier when you organize stuff this way. I don't have a calculator, obviously, so, but just trust me that we're just going to combine all that, and you get the costs for women's and men's teams. So here's some more. So we're going to do A times B and B times A. Now both these are 2 by 2 matrices, so that's great. 1, 4, 3, -2, 5, -7, 6. So we have a dimension matchup. And so the final result will also be a 2 by 2. So if I work that out, I'm going to do 1 times 5 plus 4 times 9. And then I'm going to do 1 times -7 plus 4 times 6. And 3 times 5, -2 times 9. 3 times -7 plus -2 times. And if I work it out carefully, I think I get 41, 17, -3, and -33, I think. Okay, but here's a problem. I won't say a problem, but just something to take note of. What if I reverse matrices? So now I have to put B in the left and A to the right. Now, generally speaking, if I just multiply two numbers in reverse order, big deal. They're the same, right? 4 is 3 times 4. For matrices, actually, it is a big deal. You will get a different answer. So in this case, the answer is no. That's because it's not commutative, which you might remember hearing that property in middle school. 5 times 1 plus -7 times 3. 5 times 4 plus -7 times -2. Then I do 9 times 1 plus 6 times 3. Multiplying that row by that column. 9 times 4 plus 6 times -2. So I get -16, 34, I think, 27, and 24. Much different results. So matrix multiplication is not commutative. So you do have to be mindful of the order. And we kind of already worked out example 2 here. And let's actually take a look at what happens here. If I do A times B plus C, B plus C is going to be -2, 4, -2, and -3. And just to save a little time, I'm going to do this in the calculator. You can actually maybe pause the video and see if you get the same result as I do. So you will learn how to do this when we meet as a class. There's a really nice feature in the calculator. So 4, 3, -1. And to be honest with you, I'm doing this quickly because the bell's about to ring because it's almost a B period. And maybe I'll ask you about that in the video question. So why do I have to rush? Example 2, part A. That's the reason why. -2, 4, -2, -3. So I actually do get a different answer. So what this also tells us, so I get -14, 7. There's a bell. -4, 8. So matrices are not distributed. The answer is no here. So you can't assume that either. Not distributive. Sorry for missing handwriting. So anyway, that concludes the video, and I'll see you guys later.